very exciting week. So let me now short or briefly explain a little bit what we are working on. It will probably take you in a slightly different direction. I have to warn you, maybe the slides will be a little bit heavy on math, but I will try to kind of keep the key details and not bore you very much with the mathematical expression. So without further ado, let me just shortly kind of say what I'm going to talk about. And specifically, I will concentrate on topics that is not exactly related to image processing. So we will largely focus on localizing smoke and gas sources. It, of course, has a very direct relationship to natural disaster management, as we know from forest fires. So they do produce a lot of smoke, and of course the first thing that you would like to use to analyze these fires are cameras. But at the same time, you also have a lot of information about these processes from chemical sensors. So sensors that sense levels of CO2 or CO that are produced by the burning wood. There are other chemicals that are released into the atmosphere from these fires. Also, at the very early stages of the fires, you could detect the presence of these particles or increased CO2 concentration without actually seeing the smoke, or without being able to see fire. So basically, you can use these methods at the very early stages. And the methods that we develop at my group actually target these source localization, trying to identify the possible locations of gas or smoke sources based on chemical concentrations. And the methods that we are using are largely based on so-called sparse Bayesian learning. So I will later give you a little bit of an overview what these methods are about. But before we begin, where we actually come from. So I'm from German Aerospace Center. So we are one of basically we are the biggest research center in Germany, spread all over the country. Our main interest is, of course, space domain, but also aeronautics, transportation, energy, and in very recent times, security, as you might have heard from the news, unfortunately. But these are kind of main directions in which we do research. We do, of course, primarily located in Germany. However, we have a few offices that represent our activities also in Brussels to have a better connection to European Union, Paris, Tokyo, Washington, and we are effectively government-funded research organization. So we do have some third-party funding, of course, but the main lump of our funding comes from the German government. My institute is located in the south of Germany. We are very close to Munich. It's in a small village called Oberpfaffenhofen, but basically it's a Munich area, and it's one of the biggest research centers within the DLR. So on the campus we have 6 research institutions and a number of scientific technical facilities that provide services to different operations. So, for example, German Remote Data Center is located at our premises. As you can see, maybe from the image, there is a small airport from which we also operate our research aircrafts, Galileo Control Center, Competence Center for future Galileo systems, and so on. So it's a relatively big research center in south of Germany. Our institute is not the biggest one, but we still have around 230 employees, most of whom are doctoral students and researchers specializing in effectively in communication and navigation areas. So we do a lot of fundamental research related to these topics, but also a big focus is on experiments, development of practical systems, and testing the systems in real life. more the four major topics on which we work cover, of course, communication, meaning global connectivity, so satellite communication systems, um, development of new communications standards, cybersecurity, of course, global positioning in navigation system, meaning basically everything that is related to satellite navigation, GNSS, mainly, of course, Galileo, but also GPS, Baidu, GLONASS. And one of the topics where we are particularly active is autonomy and cooperation. And this is where my group is working. And my group is called Swarm Exploration. So we are working on developing swarm solutions for different applications, primarily in space and Earth-related applications, and recently security. So why swarms? So why do we concern with swarms and multi-robot systems? So the primary objective for us is to develop future robotic systems that will be applicable in space, on orbit, on the Earth, on the surface of water, and also underwater. So we want to cover kind of really the whole domain of operation. And when we are striving for autonomy, of course, we want a system to be intelligent. We want it to be robust. We want to also have to have efficiency, in particularly if we're talking about natural disaster management scenarios. And Swarm is one of the tools that actually can address these challenges, no matter whether we talk about planets, response to a catastrophe, or security application. So this is actually a system that can provide this increased sensing aperture, new functionalities, new abilities that are in general are not available to a sensor or to a system that carries just a single pack of sensors. So this is something in Swarm that can be unique in many respects, related especially to the areas in which we're working on, and this is something that that will provide this additional sensing capability. So how do we come to source localization, gas source localization? So this is one of the topics that we, among other things, that we look at the group. And what is the idea? What is the purpose of this gas source localization? So imagine a situation in which you have an unknown number of sources that release poisonous gas or smoke from forest fires that you cannot observe directly. So you do not know how many such sources you have or where they are situated. But what you can do, you can take a robotic swarm, equip it with a number of sensors, and utilize the swarm to collect this data, process this data in an appropriate fashion in order to identify how many sources we have and where these sources are located. So this is a task that we set to solve, and this is kind of an approach that that we also apply, for example, for exploring forest fires, to trying to understand what are the possible sources of the forest fires, given the measurements that we can collect with the ground sensors or flying robots. So where you can use this technique? Well, of course, search and rescue. That's one of the applications. You could also apply it to monitor or to enforce some regulatory constraints, for example, on the emissions from the ship industry. So you can really fly into this plume and take concentration to identify what kind of fuel was burned, whether it's allowed fuel to be used close to the harbor. Of course, air quality monitoring, especially in industrial, during the industrial processing. Scientific missions is very interesting. So what you see here is actually Volcano Island, where we did experiments quite recently. But of course, that's very much related to planetary explorations and exploration of planetary body like Titan. And of course, security applications like chemical or biological events that might be dangerous to be explored by the humans, but by the robots, it's actually quite a convenient solution. How do we approach these problems in general? So what is a kind of a general methodology that we follow to try to understand how the swarm should tackle or address these problems of swarm localization? Well, the two main components that we need to make our system work is, of course, be able to collect measurements. So we need to have an accurate measurement system on the one hand, and on the other hand, we also need to have an understanding of the process that we explore. Why this is needed? This is needed primarily because we don't have huge databases which we can use to do the training. So we don't have the luxury of having a huge data set or data that has been controlled, that have been collected in controlled conditions, where we have labeled information about the number of sources and their particular location. So these data sets are simply not available. No one has collected them. So we need to kind of compensate this lack of training data by using essentially what we call a domain information or prior information. And this is typically comes from expert knowledge or from physics that explains how these processes that we're trying to understand or explore, how these processes evolve based on universal laws, basically physics. So this is kind of two concepts that are key to our processing. So once we have the measurements that we, of course, collect with our robotic system and the process model, what we effectively try to do, we try to bring these two things together. We try to understand how the model parameters can be identified or estimated based on the measurements that we collected. And that goes into effectively cooperative inference. So here the word swarm plays a key role. So we are interested in doing a cooperative inference. We do not want to transmit all information to one decision center. We would like to rely on a distributed information processing so that the swarm is intelligent on its own without having one kind of data data collection and data processing location that would kind of crack the numbers. So these are the cooperative inference is another element which is quite important for us. But we go beyond that. So once we have this cooperative inference algorithm, we also ask ourselves, okay, how good we can actually identify the parameters of the model. And this is what essentially one of the key elements which actually leads to what we call a swarm exploration. So how can we utilize the models that we have collected and the data, the models that we have and the data that we have collected to better understand what we do not know about the model or about the process, given the measurements that we already have. So this is what we call an uncertainty quantification, and you will see this in some examples, so how this uncertainty actually looks like a little bit later. But this uncertainty quantification is actually the main input into what we call a swarm movement or swarm path planning algorithm, which actually decides where we need to collect new data, where do we have to fly, so that we collect new measurement, which improve our understanding of the process, which get us a better understanding of the parameters on which we can derive new uncertainty quantification, find new locations, collect new measurements, and this is how we proceed. So this is effectively our kind of key methodologies. This is how all the methods that we develop operate on a very abstract level. The one part of this process is essentially related to, of course, inference and modeling. The other part is related to exploration and navigation. And today I will mostly talk about inference modeling. I will lightly touch on exploration and navigation, but I will mostly talk about cooperative inference and understanding of this process, because we are going to talk about sparse Bayesian learning and how to represent this process with multiple sources. All right. So at this stage, I would like to ask the moderator. So if you have any questions, please put them in the chat, and I would ask the moderators to interrupt me and ask questions, and that I will come back. But I do not see the chat window, so since there are no questions at them, or I assume there are no questions at the moment, I would proceed now with making this scheme, making this methodology a little bit more concrete, and I will begin with the first block, problem modeling. So how do we actually approach the understanding or modeling of the source localization? So as I said, we do not have a lot of data. to train our model. So we need to rely on expert or prior information about the processes and the way how we approach the model in itself. And one of the one of the approaches that we utilize in our work quite heavily is so-called a physics-inspired or physics-based model of the gas propagation. Effectively, we know that if we have a certain number of sources that are distributed in an environment, then the distribution of the gas from these sources will be affected by two major factors. So the first factor is the diffusion process. So it's a source effectively puts out the material into the atmosphere, into the environment. It can be a hot gas, for example. So the hot gas, of course, expands, and that creates, due to the temperature differences, that creates a Brownian motion, which is responsible for a diffusion of this material into the atmosphere. So that's effectively, if you will just have a diffusion, we will see basically kind of a sphere of gas propagating from a source, right? So that's kind of how the gas would propagate from a source in an absence of wind. And the wind is a second element and quite important element in making sure that kind of transport this gas in a particular direction. And as you can imagine, in reality, the wind is one of the key components, which kind of describes how the smoke or the smoke plume propagates. So if you look, for example, on a ship leaving the harbor and you see this smoke plume coming from the ship, you see that it typically goes in one particular direction. That's of course wind that drives it in a particular direction. So it's and the model that kind of describes such processes are called advection diffusion processes, and they're described by partial differential equations that you can see here. And if you kind of try to numerically model this equation, or if you try to solve this equation, let me now see if I have a laser pointer here. It's here. So if you kind of try to take this partial differential equation model and try to solve it, what you get is kind of a dynamic picture that looks like this. So you have a certain wind that changes its direction with time. So the arrow here indicates in which direction the wind blows. We have a few sources that are distributed in the environment. And the solution of this equation will be the function that you see on the left. So this is kind of a time varying description of the concentration as the time goes. And we will use F to define the concentration value. And as you can see, this is effectively, in this case, is a three-dimensional or four-dimensional function. So we have X as an input. It's a coordinate of the position. We have time that describes the change of this function in time. And the value of this function will be the actual concentration value. So it's a four-dimensional object that you can realize, that you can see here. So it's a pretty complicated structure. Of course, this is what we call the forward processing, right? So a forward model. Assuming you know the wind, assuming you know where the sources are and how many sources you have, by solving the equation, you get this nice picture. In reality, you do not know where the sources are. That's our task, to identify them. We do not know the wind typically. So these functions on the right-hand side, the V and U that you see here, are unknown. And typically we measure them. So this is where the robots are coming into play. So we take observations of our concentration values. Often we say, if we just take our robot and fly into the plume, we just measure an in situ concentration. So we just measure a concentration, a noisy concentration value. And we also have wind sensors that measure how the wind changes in time and also in space. So we need to somehow get this information about the wind, and it's a very important information for us. But this is kind of a model that we will utilize for our purposes. Okay, now I switched off the laser pointer. How these measurements are constructed? Well, as I said, we equip our drones or robots on the ground with the corresponding measurement sensors. It can be an in situ sensor. which kind of is directly put into the plume. And this in situ sensor, of course, has a certain impulse response, or actually it's a point spreading function that tells you how sensitive the sensor to a particular location. And it's not necessarily direct. We model it often like this, but it has, of course, some sensitivity in space. It also has sensitivity in time, so this is not exactly accurate model, but this is a very good approximation to this, right? So we have a certain model that tells us how we are measuring our concentration, and similarly, we also have a model that tells us how we accurately and where we also measure our wind field. So this is a kind of a measurement system that we're using. As you can see, we're having here kind of a classical state space representation, right? So we have a dynamical model that describes the process change in space and time. So that will be our dynamical system. And we have a measurement system that describes how the state, which is our concentration, is observed. So this is kind of this two-layer setup that that we will use to kind of describe the process of interest. How do we actually model the sources? So this is our kind of prime objective. We want to identify the sources that kind of model or drive the whole dynamics process. And one of the assumptions that we put here, first of all, we say, let's assume that the sources are stationary. So the sources do not drift in space or in time. So this is a simplifying assumption that helps us a little bit to relax our modeling. It's not always realistic. For example, for forest fires, we know that the fire propagates, right? So the sources are moving. But on a time scale that is relevant for us for the estimation problem, we can treat the sources as almost time invariant. So effectively, we say the sources, the functions that kind of drive the whole diffusion process, is just a linear combination of weighted Dirac impulses. So every delta here, it's a measure, it's a Dirac impulse that is located somewhere at the location theta with a subscript L. So it's kind of an individual source that is located somewhere in my space. And the scaling of my delta impulse tells me how much information, or sorry, how much material this source puts into the atmosphere, right? So this is, think of it as a release rate. How much milligrams of CO2 a particular source outputs into the atmosphere, and the particular location theta 1. Now let me activate a laser, oops, a laser pointer again. So a particular source located somewhere in my omega domain where I'm doing the estimation, and it has a certain location in this domain and a certain release rate. So I know that at this location, this source puts so much material into the atmosphere. And in reality, of course, I do not know the true number of sources. So it might be 3, it might be 5. I do not know how many I have. And the method that we have developed that kind of utilizes sparse Bayesian learning in order to address this problem of not knowing how many sources I have is essentially to use a surrogate model. It's maybe a little bit, you probably have heard on a surrogate model in a slightly different context, but what I mean here in our context is that instead of saying that I have kind of a model with a true number of sources, so for example 3 is as in this picture, what I'm saying is that instead I model my source term, the number of sources, as being really, really large. I'm saying I have millions of sources located somewhere in my domain. I do not know where they are, but what I'm saying is that I have really a huge number of these sources. So this L is very, very large. However, I require that the release rates of these sources are not all non-zero. So effectively, I'm saying the weights of my sources are sparse. So although I have millions of sources, potential sources, many of those sources that I will have in the model have a release rate of 0. So there is a source, it has a release rate of 0, but it will have no impact on my estimator, right? Because it doesn't produce any material. And only a few of those sources do not have a weight 0, so they will be active. And what I will try to do now in the algorithm, I will try to actually use this assumption to estimate the number of active sources only. And the inactive sources, so those that have the weight 0, I will just ignore. There could be a million of them, but they're not interesting. And those that are non-zero, that will be kind of an estimate of the true number of sources that I will have in the model. So I will try to estimate the L true, or the not true number of sources, by just counting how many non-zero release rates or sources with non-zero release rates I will have in my estimate. So this is how I will try to approximate or estimate the number of sources without kind of making my estimator combinatorial in the number of sources. So this is kind of an approach that we will follow. All right, so we have now the model, we have now the assumption about the sources. How do we proceed? And in general, today I will talk about two principal approaches that we have tried to address this problem, to identify the sources and their locations. One of the approaches is a completely numerical approach. So it effectively uses numerical tools to deal with partial differential equations, and kind of have the whole optimization and learning loops that I have shown before. And later, I will also talk shortly a little bit about analytical approaches that we looked lately, and these analytical approaches turn out to be a bit more computationally efficient, although they bring kind of slightly different types of problems with them. All right, so let's start with numerical approaches. So here I will try to really briefly go over the numerical approaches to solving differential equations. And in fact, you might have heard that the standard way of dealing with partial differential equations is to use finite elements methods. And the finite element methods, in essence, what it does, it says, okay, I have my functions of interest that I want to estimate. So it can be my concentration phi, which is continuous in space and time. I have my wind, which is continuous in space and time. I have my sources, which are continuous in space and time. How do I deal with that? And the first step is to say, okay, let us approximate or represent our function using some fixed and a predefined basis set. So it's very similar to a classical Fourier transform, right? Where you represent your signal in time using a linear combination of Fourier bases. It's a very similar idea here, but you do not necessarily use Fourier bases. You use a different approximation or a different basis to represent your functions. So the first step that you do, you kind of bring your PDE in so-called weak form. So instead of looking directly at the functions, you look at the inner product of your functions of interest or your equation with the functions that is typically called a test function, which is selected. So this is something that you select. So this phi of x, this is something that you select. And then often we apply a method which is called a Galerkin method, which effectively says, let's take our continuous functions in space and time and represent them or decompose them into a functional series. So this is kind of where this Fourier idea comes into play, right? So I want you to kind of think about the Fourier basis, where psi are my basis functions, which again, I select, and the coefficients of these basis functions depend on time. And my basis functions depend only on space. And I apply this to all the functions that I have in my equation. So I have them, I have actually like 4 of them: concentration, source signal, I have this test function, I have the wind velocity. And to all these functions, I apply this functional series representation. Again, based on the functions that I select. And these basis functions that I select, this is something that we called finite elements. So these are functions that are well localized in space. So they have effectively 1 at one particular node in space and 0 everywhere else. So they are orthogonal in space. And if you kind of create these functions, then what you typically get is this classical mesh type discretization, where one of the these finite element functions you see here is shown here in color. So it has a center where it's 1, and at all other nodes, this function is 0. And between functions, just planes, right? So it's kind of you can think of it like a pyramid in a space. And this is a function that you use to represent your space. So it's effectively a discretization of the space. And the summation of these functions or finite elements, this is something that will, at the end, give you a reconstruction of the functions that you're trying to estimate. And the unknowns in this representation are the coefficients. So these are these time-dependent coefficients which which represent a decomposition or representation of your continuous function as a linear combination of these fixed finite elements. So the coefficients that we are actually trying to estimate are these linear representation coefficients of our function. So these are our unknowns. And as you can see, they all depend on time. So we have let me shortly jump back. So we all have this time dependency, right? And time is still continuous. So it's still a continuous time coefficients that are now discrete in space. So we now discretize the space. How do we proceed? Well, basically, we come back to this weak form formulation where we have this inner products between all our function and the test. And if you write it down and plug now instead of function our approximation, we end up actually with a discrete representation with matrices. So we have vectors and matrices that will represent all these inner products. And if we continue to do so, then we can apply it to all terms that we have, to the source term, to the time derivative, to the diffusion term, to the advection term. So we can do all these computations, and effectively we end up with an equation that is continuous in time, but now discrete in space. And as you can see, we have here matrix vector products. It's a little bit complicated structure, but at the end of the day, it's a vector matrix type multiplications. And the final step is, of course, to bring it all into the discrete time by discretizing the time. And if we do everything properly, we end up with a difference equation that describes our advection diffusion now in a discrete domain, right? So we now have a state space representation, which is no longer a partial differential equation, but a difference equation in space. Difference equation in time, and the vector describes our discretization in space, and that's kind of starts to look in a little bit more like classical Kuhnmull filter state equation, right? We have a state at time n, which depends somehow on the state at time n minus 1. So this is kind of the direction in which we are going. And of course, we need to also introduce a boundary condition for partial differential equation, which basically kind of extends the state space with additional variables. But that's just a minor thing, so that's not that important for our discussion. What is important is that we take a continuous equation in time and space domain and effectively bring it into a difference equation over a large state space vector, which describes our state or system in space now. So we now have basically a fully discretized equation. How do we proceed from there? Well, as I mentioned, we are going into sparse Bayesian learning. So how does the sparse Bayesian learning work? It's a Bayesian approach. So we need to kind of get rid of this classical standard deterministic approach and put everything into a probabilistic framework. How do we do that? Well, first of all, we say our equation, so our advection diffusion or PDE equation, does not hold exactly 0, but rather it has a certain residuum. So it holds approximately, and the residual signal follows a normal distribution. So we say the concentration value that we obtain is effectively describes a certain probability distribution. So it's a probability of our concentration, which is conditioned on the wind and the sources. So if we know where, in which directions the wind blows, and where the sources are and how many we have, effectively we can just solve the equation by just iterating it, and then we have a solution. It's a forward solver, quite simple. And if we solve the equation, we'll get our concentration. But of course, the equation does not hold exactly. So we say that the residuum that remains is random. And that's give us our probability distribution over the concentration value. Of course, we have measurements, right? So we have our robots that measure winds, that measure the concentration of the gases, and that give us effectively what we call the likelihood, right? So that's a probability of a measurement, which is conditioned on knowing the wind vector and the concentration. Again, that's given by our measurement equation. And this is where the sparse Bayesian learning comes from. We need to also define the prior distribution for the wind and for our sources. So if we start bringing in kind of all pieces together, we would like to estimate concentration. We would like to estimate wind and the sources given our measurement. So that's, we would like to come to a posterior distribution of these unknown parameters given what we measure. And if we write down this posterior distribution, we see that it will actually contain a state likelihood, which tells how our wind and concentration impact our measurement. So that's our measurement model. We'll have our partial differential equation model now in a probabilistic context, which tells how the concentration probabilistically now depends on the wind and the sources. And finally, we need to specify a little bit of a prior about the wind and the sources. So let us look a little bit deeper into that. So for wind modeling, we typically follow a very simple assumption. So we say, well, we first of all do not distinguish between laminar and turbulent components, which is a huge simplification, but we need to do that because otherwise we would also have to deal with Navier-Stokes equation, and that will make our life really, really difficult. So, so we use a simplifying assumption by saying there is no turbulence. And we also say that the X and Y directions of wind are statistically independent. So this is kind of one of the main approaches that we follow. And the only thing that we need to know is the mean of the wind and its variance. And these are parameters that need to be selected for the prior. And these can be actually obtained, for example, from the weather forecast. So we know the dominant wind direction, and we can use this information from the weather forecast to construct these priors. And in this way, we can then define the prior for the wind. For the sources, this is where the sparse Bayesian learning comes into play. So how to model sources? So when we started with the discretization in space, we have a vector U, which describes where our sources are. And this is kind of the discretizations that we have chosen before. And of course, it depends on time. So we will have a vector that might, those are sources that might change in time. As I said, so our main assumption is that we have a lot of sources, but some of them are non-zero. The rest is zero. This is what we call the sparsity assumption, right? So the source vector is sparse. That implies if we look inside this vector, we see a lot of zeros, and only on some locations are non-zero values, which you see, which you actually see here, right? So this is a non-zero value, this is a non-zero value, these are all zeros, and this is another non-zero values. So in this case, we could say, okay, we have a vector has n components, so it's a very large vector, which describes the whole discretization of our spatial domain. But there are only 3 components that are non-zero. So this is how we model it. And our goal is actually to identify which components will be non-zero here. And the sparse Bayesian learning does it indirectly by introducing a hierarchical prior that will result in an estimate that is sparse. And this is done by introducing additional parameters, which are called hyperparameters. And these hyperparameters control the contribution of a source to the model. So it actually is these hyperparameters that decides whether we have a source or not. So it's this hyperparameter will have a strong resemblance to detector. Effectively, its value will tell us whether the source has to be set to 0, there is no source, or the source is non-zero, and then we'll have a value that that we will use as an estimate of the source release. So this is how the sparse Bayesian learning will operate in order to get to identify which sources are relevant for us. Let us look a little bit into more details how the sparse Bayesian learning is working. So effectively, we construct this hierarchical prior, which consists of two contributions. So one is a Gaussian contribution, which says that the source value given this hyperparameter gamma is a Gaussian with 0 mean, and the actually it's an error. It has to be a variance. So it's not 1 over gamma. It's just gamma I, which is a variance of this parameter. And this hyperparameter itself follows a gamma distribution. So it's a slightly strange combination, but if you look how these hierarchical prior actually, or what is an equivalent prior that you use, and you can actually kind of marginalize over gamma, and you find that this is actually a student T distribution. And what is important here is that if you look closely, it actually looks a little bit like an almost like an L0 norm. So if you kind of plot an L0 sphere, you would see that it's a pure cross. L1 sphere would be a rotated, it will be a rhombical structure, right? So it will have, it will go basically like this for L1. And the student T is something in between. So it's a kind of a distribution that places probability mass along the axis. And that's what will effectively make the estimator sparse. So the difficulty is, of course, here we have this extra parameters that we need to estimate. But let us look maybe a little bit further on an example that will highlight what happens here. So imagine a very simple estimation problem, right? So you have a linear model. You are trying to estimate parameters U1 and U2 given some measurement. So if you just plot the model, you would see it's just a line, right? So we have kind of a parameter space with U1, U2. It's just a line. And we are trying to identify these parameters U1 and U2 based on the measurement. So the simple solution or classical type of kind of regularization that you would need to use here, because you have just one measurement but two unknowns. So you need to regularize the problem, and one of the ways to do that is to say that the solution has to be smooth. So you use an L2 prior, which is effectively a circle. And if you apply this prior, this is the posterior that you would get. And of course, the maximum of this posterior will get you to solutions. So 0.2 and 0.3. And as you can see, you have two solutions. That would be kind of the maximum solution, which would kind of place you somewhere here. And that's typically the solution you get if you use a PINF in MATLAB or in pseudo-inverse or ridge regression in Python or in MATLAB, doesn't matter. But ridge regression, that's the solution that you would obtain. As you can see, it is not sparse. But if you use the sparse Bayesian learning for that, then situation will be slightly different. So again, the same situation, the model is the same, but we use now a student T distribution. And if we now look at the solutions, and all of a sudden, the probability mass collapses on the axis. So we see there are two possibilities where we would have a solution. One of them on this axis, and other them on this axis. Maximum will be here, but all of a sudden, our solution is sparse. So we find only one solution that has one coefficient 0.5 and other is 0. So we have a sparse solution. And that's the difference between using this student T or hierarchical prior and using standard ridge regression-based approach. So this is kind of an approach that we are going to use, and why sparse Bayesian learning can be used to not only obtain a sparse solution, but also to identify how many sources we have. So now let me walk you briefly through the estimator. Of course, we now have a lot of parameters that we want to estimate. We have the sources unknown, we have concentration that is unknown, wind, hyperparameters, only given measurements. And all these parameters are given by the corresponding probability density function. So the model fit is given by our measurement equations. Model is our PDE, sources and hyperpriors, our things that we have just defined. And one approach to kind of model this system is to use classical hidden Markov structure, right? So we have kind of initial state of our concentration, which transitions to another state because we have a time-varying process. We have some measurements of the concentration. We have some measurements of the wind. And if you kind of bring all these parameters here, we have a dynamical system that tells us how our concentration will change over time. And our goal is, of course, to estimate these parameters. So we need to run an inference over this model. And one of the ways to do that is to use factor graphs, because everything kind of factorizes quite nicely. So the solutions that we have developed for such type of problems are factor graph-based solutions. And the factor graphs, or the advantage of the factor graph is that you can derive messages that you need to send between factors. By basically transmitting the messages between the factors, you can then identify the marginal PDF of the variables of interest, of the concentration, of the source values, or of these gamma hyperparameters. So you can obtain an estimate not only of the mean values or just to estimate values, but you get the distributions. And that's quite important because that kind of goes from the model fit to the uncertainty quantification, because the distribution of the parameters, this is something that tells us how our parameters are uncertain. And since we have the parameters are actually representing coefficients over space, so it's a discretization coefficients that represent our spatial or continuous functions, we can actually plot the distribution of uncertainties over space that we are exploring. And this is kind of the tool that we use to define the exploration strategies. So how the exploration strategy is defined. So we have kind of this probabilistic inference that utilizes factor graph by just transmitting messages. Of course, we feed the measurements into the system. And by doing this probabilistic inference, we come up with the source distribution, so the means of the estimated factor graphs or factor values, but also with the concentration distributions, of course, but also with uncertainties, because we not only know the mean value, also the whole distribution. And what we can do now, we can actually measure the size of this uncertainty and say, okay, every cell will now have a different uncertainty. Some will be higher, some will be lower. So those uncertainties that are high are interesting for us because this is something that we do not know about our parameters. So this is probably something that where we want to go and measure. If the uncertainty is low, then our measurement have sufficient information about this particular value. We don't want to measure there. And this is kind of the strategies that we follow. How does it work in practice? Well, this is a simulation now where we say, okay, we have a wind, which we say we know. This is a concentration of the field that we know. And we compare two strategies. So one is this rich regression-based approach that you see in the middle column. And on the right, you see approach that kind of uses the information about the sparsity, the Sparse Bayesian learning approach. You see also the discretization here, so the mesh that has been created, and we measure in the nodes. So we measure exactly where the nodes of the mesh are located. So we will compare what will happen after the 10 measurements. So you see where the first strategy has placed its measurement according to the maximum of the uncertainty or the information. And here you would see the estimation of the concentration. So the upper row is a concentration values. The lower row is an estimation of the source locations with the corresponding uncertainty. So let's move on. So after 10 measurements, you see that for the informed strategy, the algorithm actually prefers to go down the wind, which actually kind of makes sense. For the uninformed strategy, it looks like we measure everywhere, and it's turns out to be not a very good strategy, because after 30 measurements, informed approach already identifies the first source, and gets very close to the estimation of the concentration for the one of the sources, and start kind of moving toward the second source, while the uninformed performs significantly worse. It's kind of covers, it basically does a coverage solution, and that doesn't look very good. With informed strategy, after 50 measurements, you already get the true sources and the concentration values very, very accurate, while the uninformed still relatively far away. If we proceed further, we see that uninformed start now doing coverage because it has discovered everything. It knows where the sources are. It knows the concentration value quite well. And what it does is now kind of explores further, where uninformed strategy continues with this approach, and only you see slowly correct estimates are appearing. And basically you catch up almost after 250 measurements. So it's a factor of effectively 5 that you save if you do this information-driven approach. If you kind of do the simulations, you see that you are significantly faster if you utilize this assumption that your sources are sparse, that you have only few sources, both in kind of concentration error reconstruction, so you're significantly more accurate in reconstructing concentration, but you're also more accurate in reconstructing the support. So this EMD, it stands for Earth Movers Distance, and this is a measure that measures how accurately your sources are reconstructed. And you see that you actually significantly better and faster in both in both of these metrics. This is just a small example of the strategy running in an experiment. We have here 5 robots that implement this strategy in real time. It's a decentralized approach, so the robots do not send the data to a communication center. They do not know where the sources are. Of course, it's a laboratory experiment, so the measurements of the gas concentration are synthetic. We just take from a simulation the corresponding concentration measurement. But as you can see, after roughly 4 minutes, we are able to identify the true number of sources and their locations. Although in the beginning, the number of sources changes, but at the end of the day, the true number of sources and locations are identified quite accurately. We repeated these experiments also in laboratory with real gas. So what you can see here is ethanol, and robots carrying ethanol sensors. So it worked actually quite well. It's of course not that fast, but let me now just go briefly through the experiment. So you start again collecting the measurements. You follow the exploration-driven approach, trying to estimate both locations and concentration. Also, you try to estimate the wind at the same time. And as you proceed, you see that you are to start kind of identifying the first source, which is slightly off from the real one. But it's basically within one discretization cell of the real source. So they are pretty close. And then after 11 minutes, you identify the second source, or also quite accurate. So the method works both in simulations with a hardware-in-the-loop as well as with real data. But that, of course, requires solving these partial differential equations numerically. If you start increasing the dimensionality of your domain, it turns out that you do need a lot of discrete cells. And all of a sudden, the dimensionality of the problem becomes quite significant. So the question is that possible to somehow make it more efficient? Kind of get away from these solving partial differential equations numerically. And this is a relatively new approach that we follow, and it's kind of I call it analytical method, but in fact it is semi-analytical, and I will explain in a minute what I mean by that. So what is an idea of dealing with of doing this analytical methods? So one of the disadvantages of the gridded methods or numerical approach is that, first of all, your vector that represent your sources has a dimensionality of the discretization of your domain. So if you think about even a modest domains that you're trying to approximate, like let's say 1,000 meters by 1,000 meters, you discretize it with 10 meters per cell, which is a relatively large cell size, right? You end up with 100 times 100 cells on the ground. And if you just go in a third dimension, all of a sudden you have already 10,000 times the discretization in the third dimension. So if you have at least 10 cells for the vertical component in 3D, you end up having 1 million unknowns. And the algorithm doesn't know where which elements are zero and which are not. So you have, and this is just one of the vectors that you estimate, right? The source vector. You also have a concentrations that you need to estimate, and the wind that you also need to estimate. So the dimensionality of your problem becomes very, very significant. And every number that we have in these vectors is an unknown. And basically, for estimating an unknown, you need a measurement. Of course, we have a regularization, the sparsity-based regularization, so we do not need as many measurements as unknowns that we have. But it's a huge number of unknowns numbers, so we need to have sufficient number of measurements to get reasonable estimates. So the numerical complexity of this approach is the number of measurements tend to actually grow quite fast for large models. We also have to keep in mind that in order to solve the partial differential equation, we typically need to solve the least squares problem. And its dimensionality depends on the number of unknowns that we have. And that grows, if you kind of do it in a straightforward fashion, it grows like an n cube with the complexity of your problem. So the question is, can we kind of bring down this complexity a little bit? And one of the approach to do that is actually to go off the grid. So to say my parameters are not on the grid. My source is parameterized. It's not discretized, so it's not tied to the grid, but it's just parameterized by a few parameters. Its position, which can be a 2D vector if the source is located on the ground, and its release rate, right? So per source, I have 3 parameters, 3 unknowns that I want to estimate. And if I have a number of sources on the order of 3 or 5, which we would typically have, then in total, we have like 10 parameters to estimate. So this is nothing in comparison to millions of unknowns that we have for the gridded method. So the dimensionality of the problems that we have to deal here is significantly lower. Of course, we do not know the true number of components, but we expect that the true number of components is relatively low. So even if it is 50 or 100, we are still significantly lower than the complexity of the gridded method. The price we pay here is that we no longer have a linearity, because our model will depend non-linearly on these parameters. So we will not have a least squares problem. So we'll not have a linear estimator like we had for gridded methods. We will have a non-linear estimator that will depend non-linearly on these parameters. So that's the price we pay for this lower dimensionality. Does it pay off? Yes, in some senses or in some cases, but not necessarily, not always. So there is a trade-offs. But in general, it can be, in some cases, it can be indeed very useful and more and significantly more efficient. So how to approach an analytical solution if we go off-grid? And one of the methods, analytical methods to solve PDEs is a so-called the Green's function-based method. So what is a Green's function? Effectively, the Green's function is a concept that is actually well known to any engineer who had a course on system theory or linear system theory. Because if you think about a linear time invariant system, the first thing that you learn in theory about those is a impulse response. What is an impulse response? So if you have a linear time invariant system and you kick it with a Dirac with an impulse, the system produces an output which we call an impulse response. And we say that if the system is linear time invariant, it adheres to superposition principle. So it can we can then predict or compute the output of the system to any number or linear combination of the impulses by just linearly combining corresponding impulse responses. So the system can be studied in terms of this impulse response. And the green function is nothing different. The Green's function is effectively a response of a linear partial differential equation to an impulse, which is now a Dirac in time and space, and the system response, it's more complicated in this case, but it's still a response of the system to an impulse, and this is what is typically called the Green's function. And a complication or a complication in connection to the impulse response is the fact that this will typically depend on a particular partial differential equation, and more strongly or very strongly depend on a particular domain in which this partial differential equation is computed. And unfortunately, these functions cannot be computed for arbitrary domains and arbitrary partial differential equations. Exist only for certain domains and certain partial differential equations. At this moment, can you please confirm that you can hear me? Because I had an incoming call and I'm afraid that the connection got broken. Hello?
Yes.
Okay, so I will continue then. So the idea is basically the same. It's an impulse response of the partial differential equation. And for us, it's quite useful because the right-hand side for our equation is a sum of impulses, so sum of individual sources. So if we know the response of the Green's function for a single source, we can now compute the concentration for any number of sources by just adding those functions up. And that's how we will approach the solution of the partial differential equation now, not numerically, but using the Green's function. So we compute the Green's function, and then we just see how the concentration is constructed as a linear combination of those. All right, so let us go back to our partial differential equation, which P here now indicates the position somewhere in the space. T stands for time. So that's the same equation that I had before. Its right-hand side is a sum of Diracs subject to some boundary conditions and initial conditions. So for example, we say at the boundary, our concentration disappears, and at time moment of 0, we had a certain concentration level in the room. So this would be kind of a numerical solution that you see here. Unfortunately, that would be already the case where you cannot compute the Green's function analytically. So that's where the Green function, computation of the Green's functions will be impossible in general. You can, however, simplify it by saying, for example, that my equation is time invariant. So you consider a stationary case. And you also say that the domain over which you compute your function is infinite. In this case, you can actually find a Green's function. And it is shown here. It has a relatively complicated form, but effectively it's a form that you can still compute analytically, and you could see how it will look like. So how a response of this function will look like for a single source. So you have a source here, and you see this contour lines that describe how the concentration changes in space. And you can then use this Green function as a solution. So you, again, discretize your space. Now, you can use, again, finite elements or any other discretizations that you want. You collect your concentration in a vector. You collect your Green's functions in the corresponding vector. You construct a solution as a linear combination of these Green's functions, but you do not locate your Green's functions on the sources on the grid. Again, you have a very similar observation matrix as we used before. So this is a very similar step. Again, you have kind of a state space representation. You have a dynamics that is described by your Green's function now, and you have your measurement model which describes your measurements. And this is kind of an input into, again, using the same approach as we used before. So the same probability density function which contains of the likelihood and measurements. It contains a PDE model which we now describe in terms of the Green's function. It has this constant or any other prior assumption about the source locations, and we have this SBL prior that also that we used before. And the optimization strategies that we use here is actually a nonlinear optimization that contains two steps. So the first step is a standard sparse Bayesian learning, as we used before, with the source location fix. So we say we fix the location of our sources; they are known. And what we are doing for this location, for these sources, we apply the sparse Bayesian learning to identify which sources are active and which are not. So we start with a very large number of sources, like 1 million. We fix them. We do the sparse Bayesian learning and identify which sources are zero and which sources have a non-zero release rate. And then we go into the nonlinear optimization problem, where we say the support now is fixed. So we work only with active sources, but now we allow to move these sources through our omega domain, so through our exploration domain. So we move these sources, we find new locations, and then for these new located sources, we do SBL. And this is an iterative optimization. It's a nonlinear scheme, but it seemed actually to work. So let me show how this is optimization solved in a distributed fashion. So what you see here are three sources. We have a fixed wind information going in one particular direction, and we have 4 agents kind of covering the whole information here, or the whole domains that we are exploring. So as you can see, this curved trajectories kind of cover the whole space, and on the right side you see how the number of sources changes as more and more information is collected. So initially, as you can see, we start with a very large number of sources, and then the number of sources slowly changes as we relocate them and do the sparse Bayesian estimation, and we end up with an exact correct number of sources at correct position, making the estimation correct. You can go a little bit further. You can analyze this estimation problem theoretically. You can derive Cramér lower bounds, which kind of tell us how accurately we can estimate the sources, how many measurements we have, or what we need to collect to estimate the sources, for example, with the accuracy that is comparable to the accuracy of our discretization. But most importantly, we can compute these functions or these characterizations based only on our Green's function solution, so based only on the solution of the equation. And we can use this information to use uncertainty-driven exploration. So that would be kind of an equivalent to this information-driven approach that we developed for numerical methods, but now for the analytical methods in hand. So I'm almost at the end of my presentation, so I will just, this is the final slide where I would like to summarize what we did. So it was, I know it was extremely fast and it was a lot of information, but I hope you got kind of the main message that you can approach these problems from numerical perspective, and also you can develop some analytical methods trying to identify the number of sources using now non-visual information. You can, in both cases, you can derive information-driven strategies to guide robots to better sampling locations, and that can significantly accelerate source identification. So you can basically collect more informative data samples. Both strategies can be implemented over the network of agents, so you do not require a centralized scheme, centralized computer to do these numerics, and thus quite well scalable to swarms. Green's function methods is very effective. However, you cannot really compute it for arbitrary domains. So you need to effectively approximate the solutions, and neural networks can be actually quite effective in doing that. And we are currently looking at physics-inspired neural networks to approximate green functions for general domains, but also the so-called Fourier neural operators that are particularly well suited for partial differential equations to do these approximations. And one of the things which I a little bit touched in the talk is the wind. It's an extremely important component in order to better understand how the smoke and gas propagates, but taking into account the wind can make kind of models extremely nonlinear. And at the end, would need to kind of couple the advection diffusion with Navier-Stokes equations. And that would lead kind of to full-blown computational fluid dynamics simulations, which are extremely, extremely complex approaches. But this is something that we still need to tackle, and that's something we need to keep for the future work. With that, I would like to thank you. Sorry for taking a little bit more of your time. And if you have any questions, please.